right. Well, good day, everyone. Thanks for dialing in. Thanks to the organizing committee for the invitation. I certainly appreciate it. I was asked to give a generally instrumentation-centric talk, which is why I submitted this very vague title, but I'll try and hold things together in the spirit of that title nonetheless, all the way through the talk. What I'd like to do generally is sort of summarize where we stand from a technological standpoint, which excuse me, but also turn this into a broader discussion. And so I have, I don't know, hopefully around 30 minutes of material, and I'm hoping the last whatever is left can be used for a group discussion on kind of paths forward and how we can improve as a community our understandings of the instruments that we already have. We have an entire generation of PRV instruments more on the way that I think we're only really scratching the surface on when it comes to understanding systematics, bounding individual error terms, et cetera, et cetera. So I'd like to dedicate at least some time at the end for a group discussion on that. All right, so let's start with a figure that I'm sure everyone has seen before, or some incarnation, and uses for their own purposes in one way, shape, or form. So I'm going to use this to emphasize my own point, which is that we have indeed hit a measurement precision floor, which is to say we've really hit a detectability floor. I think we can all appreciate that this floor is both astrophysical and instrumental. So looking at the last, and this is actually wildly outdated at this point, but the last few years of radial velocity measurements were, sitting somewhere around 50 centimeters per second in terms of recovered velocity amplitude. I'll get rid of my zoom window here for a second. So I bring this up to emphasize the sort of technological absurdity almost that is the measurement that we're trying to make. So the little red arrow there I've highlighted on the right is 30 centimeter per second velocity assembly amplitude. That's about a part in a billion frequency shift that we're trying to measure on this, celestial burning ball of gas. And so, of course, that implies we need very stable instruments and obviously a much better understanding of the star astrophysics as it stands now. This actually is a slide I've been using for years, as evident by the fact that I haven't updated it in 3. But I want to amend the statement at the bottom. Rather than saying necessarily near term we need more stable instruments, I would argue that that's not working. I would argue we actually need a better understanding of the instruments we have at this point. Many of us have spent a good deal of time, effort, and resources developing what is now the current generation of precision radial velocity instruments. And we need to understand them better if we are to both inform the next generation, but also squeeze every last centimeter per second of precision out of what we have. I think the success of this field moving forward as we approach this sort of 10 centimeter per second holy grail of the velocity assembly amplitude recovery at, n sigma or whatever, the success of that endeavor really hinges on our ability to understand the instrument behavior and, of course, stellar astrophysics. So to drive home the scale of the technological challenge, this is an image highlighting the measurement as seen by the measurement device, i.e. our spectrometers. So this is a very zoomed in image from an electron microscope. This is a TEM image of a blank silicon lattice, much like the materials used in our CCDs. So if we sort of solve for what I'm going to call like a velocity plate scale of a typical high resolution EPRV spectrometer, let's say it's about R of 100,000, we get something like a 6 centimeter per second per nanometer velocity solution, basically. That is the dispersion in units of velocity. And so if we map that to our zoomed in silicon lattice image here, that ends up being something like 4 to 5 silicon atoms in spacing. This is really a comment on the repeatability of the measurements. Of course, stars naturally, be given their barycentric velocities, will float back and forth across our arrays. And so it's not like the stellar spectrum is stagnant and only moves a few silicon atoms. No, this is a comment on the repeatability required and the trust we have to have in that repeatability to confidently say we have indeed recovered a 10 centimeter per second signal. I would argue moving forward that the next phase, at least instrumentally, is that we really have to be at sub 10 centimeter per second calibratability. And in that case, we go from looking at the sort of silicon lattice as a whole to individual silicon atoms. That same plate scale, if you convert that to a centimeter per second, I think hits roughly the outer diameter of the outermost orbital shell of a silicon atom. And so that's, again, the repeatability that we're aiming for instrumentally. We can get there astrophysically, great, but instrumentally, that's where we need to be, I think, moving forward if we want to continue to improve our measurement precision overall. Okay, so stepping back to the radial velocity measurements themselves, this is an entirely incomplete summary of all the effects, statistical, instrumental, astrophysical, that keep me up at night, and I'm sure many people on this call. This is all, I'm sure, appreciated by everyone here, given that we span a wide range of disciplines. Everyone's investigating their own subset of these issues. But in this talk, I'm, of course, going to be focusing on the central box, which is effectively, how do we better characterize our measurement system, and how can we improve our measurement system in general? And I'm really hoping that both the rest of this talk, I can give you kind of a sort of a mile-wide, inch-deep overview of where things stand, at least when it comes to instruments like NUID and a little bit of KPF, spoiler. But I'm hoping we can focus the subsequent discussion mostly on how we can, as a community, do a better job of characterizing our systems. So in the scheme of trying to characterize our measurement floor from an instrumental perspective, this is a typical example. I've cartoonified this a little bit just to make it easy to digest, of a radial velocity error budget. I'm not a huge fan of the term error budget. I feel like that implies you're allotting values to each one of these and then changing them as you see fit. I would say this is more of a quantitative assessment, a rolled up quantitative assessment of what our error should be based on informed modeling, experiments, etc. Doesn't quite roll off the tongue as well as budget, but whatever. And I'd like to highlight a few key areas where we've tried to make progress through dedicated testing to either quantify or bound individual error terms. So things like, how does our detector affect our measurement? How does our guiding on sky affect our measurement precision? How does the thermal stability of our system affect the measurement precision? These are all the kinds of questions that, as an instrument scientist, I'm most interested in trying to bound and, again, use as sort of motivation for either implementing new corrections in software or engineering, perhaps either for the current generation of instruments or for the next. And so I'm going to sort of walk through, again, at a reasonably high level, some example case studies for some of the elements in these boxes where we know that some aspect of the spectrometer or the fibers or the fiber injection system is indeed contributing to our radial velocity error. And the goal is really to try and quantify that using the facilities that we already have. So let's start this kind of high level walkthrough. So I want to start off with describing some of the errors associated with our detectors in general, and I'll preface this by saying all of the tests and experiments I'm showing here, for the most part, are restricted to optical instruments using classical CCD architectures, seeing limited, etc., etc. I'll touch on some of the more exotic design features of other instruments later, but for the most part, all the results I'll be showing here are mostly NUID-centric. And so the detector issues that we are up against are, well, there are many. These slabs of silicons that we love so much are highly imperfect recorders of incident photons. They have non-uniform pixel architectures. We like to think of these as discrete pixels that are perfectly square and infinitely deep with infinitely high potential wells. That is flawed, of course. They have their own characteristics just when you're injecting heat into them, i.e. when you're reading them out, they can deform and induce some level of spectral shift, or rather shifting under the spectra, I suppose. They are imperfect at shuffling charge. They're amazingly good at shuffling charge, but at the level that we're talking about, sort of tilde centimeter per second mark, basically nothing is perfect in the system, and this detector included. And so this inefficiency of shuffling charge actually can manifest as a radial velocity systematic, and I'll go into some more specifics of that in a bit. The last example I have, and again, this is just a incomplete collage of some of the things that we worry about. Detectors themselves can act as periproetalons, and so we get a lot of fringing, especially at redder wavelengths, which is sort of just a fundamental barrier. We have implemented solutions for this in various instruments in various ways, but the entire silicon slab is itself kind of an optical surface, and that's a problem in this case, especially when you're talking about red wavelengths. Okay, so let's sort of dive in. The first thing I'll talk about is something detector specific, and then we'll kind of walk backwards through the optical system back up to the telescope, etc. But to start with, let's look at a case study of the NUID detector specifically, where we tried to quantify the effects of this inefficient, imperfect charge transfer process. And so in general, as you're shuffling charge across the CCD in either direction, whether it be along the serial or parallel registers, spectral or cross-disperse, the primary spectral direction or the cross-disperse spectral direction, you're going to get some smearing of the spectrum. So what I've shown here on the lower left, on the lower right, is an example of simulated data where I've cranked up the charge transfer inefficiencies significantly. Highly unrealistic, but I think it gets the point across, where as you're shuffling this perfect incident spectrum about your CCD, you can actually mess with it in different ways. And so as you're shuffling it in the cross dispersion direction, you're going to blur it out, obviously orthogonal to the primary dispersion direction. That causes a measurable blurring. And as you're shuffling it then in the spectral direction, you're actually changing the net center of mass of your entire stellar spectrum slightly in a very biased way. And so this effect can be particularly insidious because if the inefficiency were a fixed number, let's say you shuffle charge, for every 1,000,000 photons you shuffle, you lose 1. That's modelable. The annoyance here is that the efficiency of that shuffling is actually strongly flux dependent. And so there isn't really an analytic solution to this. You don't know at the end of the day when you're looking at your recorded spectrum if charge that you're seeing was left over from a previous shuffle or was indeed part of that pixel, just because of this strong flux dependence. And so it's pretty obvious, I think, how this can be a problem for precision radial velocities, but we set out to try and bound this issue using NUID in exactly the way that is most relevant to the precision radial velocity error budget. Namely, we of course characterize this effect in the lab separately off of NUID, but ultimately wanted to understand what is the radial velocity error incurred by this effect. And to do that, we performed a dedicated test using the NUID, well, a couple of different NUID calibration sources. In this case, it's the NUID Etalon, which I'll talk about a bit more later. And so for this test, we specifically took a series of back-to-back sort of chunks of Etalon data at different signal noise values. Again, I mentioned before that it's a very signal noise dependent effect, and so we should see a clear systematic trend between high and low SNR spectra. On the upper left shows kind of a snapshot of the exposure sequence. Let's see, that's an exposure time, not SNR. But it gives you a sense of the dynamic range we're probing. And so the flux levels in our calibration spectra span the dynamic range of something like 200. And so between those chunks, again, for the same underlying spectrum, we wanted to quantify how much does the spectrum deviate just because of CTI. And so the center panel I'm showing is the measured effective radial velocity drift of those Etalon spectra, again, taken at this really wide range of signal noise values, going from very high on the outer edges of that center plot to very low. And those are color-coded by fixed signals noise. And so it's a little, you can probably pick out a systematic trend by eye if you look hard enough in the raw data. But if I bin that data by signals noise, we arrive at the plot on the lower right, which shows, again, for the same underlying spectrum, you get this clear systematic trend towards, well, larger RVs at lower SNR. And these are the types of things that we really have to quantify, again, as we march towards this sort of, say, few centimeter per second level instrumentally. Diving a bit deeper into this measurement, I know we're going to go into the weeds, but this is the only one that I'll go deep into the weeds on. I think it's helpful to sort of preface these measurements by understanding the geometry of the NUID spectral readout. So on the left, I'm showing the, I'm pointing as if that matters. On the left, I'm showing the readout configuration of the new detector. So with NUD, we have a large 9K by 9K chip. It's sort of split into two halves on top and bottom, as seen in this frame. Each half has a series of 8 amplifiers, and those 8 amplifiers read out in different directions depending on where you are relative to the center line of this array. And so those red arrows are showing us which direction each of these read out. Each of these discrete amplifiers reads out. On the right, I'm showing, this is just a PowerPoint overlay, but it gives you a sense of where the NUID's two raw 2D spectra sit on this amplifier configuration. And so we're roughly about centered, and you can see about half of each order for any given order sits on one half of the array, reading out in one direction. The other half of each shell order reads out in the other direction. And so we actually expect the CTI bias to be different for each half of each order. And so to probe this, and again, to try and perhaps verify that this is indeed CTI that we're measuring, because there are a lot of effects that could affect, or that could show up with a systematic trend towards lower signal noise, we can do one level of more detail in our analysis. So to do this, we could do things like, okay, we have high precision Etalon spectra for basically every one of these amplifiers. And if we split those amplifiers and bin the data by basically proximity to the edge of an amplifier, we can get some further constraints on the effective CTI and excuse me, and also again just verify this is CTI in the first place. And so on the left, I'm showing kind of a cartoon model of how this process went. So we picked Etalon features that were basically close to their respective amplifier readout columns, which should basically means that they have very few pixels to traverse. And so we expect this effect to be relatively small. Those are the red swaths on the left there. We can also compare those velocities to velocities for lines that have to traverse many pixels. And so that's in the sort of cartoonish view on the right. Those are the green lines. Those are Etalon features and bits of the calibration spectra that have to traverse many, many pixels. And so you expect the CTI effects to be much worse for those pixels versus the ones right near the register. And on the right, this is just to basically say that's exactly what we see. And so for bits of the calibration spectra that are near the readout register, again, the CTI effect is minimized. We don't see a really strong radial velocity trend between high and low SNR, but for pixels that are far away and have to traverse thousands and thousands of shuffles before being finally read out, we see this very large systematic trend, and that axis is correct. This is a many meter per second signal. Again, this is kind of a contrived experiment, but it's meant to show that we are indeed seeing CTI, and this is going to help us bound the overall contribution to the noise floor. Conversely, again, remember I mentioned that the two halves of the array read out in opposite directions. If we do the same experiment on the other half of the array, we should have the opposite bias. And again, that's basically exactly what we see. And so bits of the spectrum, portions of the order that have to traverse long distances have now a positive velocity offset just because the readout direction is in the opposite way. And so that was a nice verification. So I bring this up really as just as a case study for some of the experiments that we try to do with NUID, but I would argue that I think a lot of teams should be doing this. A lot of teams have done this. I think disseminating the results to the community is helpful. I think there's a lot to be learned from small experiments like this. One other feature, and this is kind of even deeper in the weeds, one other feature of this data set is that we can also perhaps, and I haven't verified this, but perhaps probe the sort of finite, the pliable boundaries of individual pixels. And so one of the artifact of this study is we've discovered that the effective width of the PSF, as seen in our calibration spectra, also varied as a function of SNR. This is perhaps consistent with what's called the brighter fatter effect, which I won't get into specifically, but I think this is another area where this has yet to be, I would argue, reasonably well quantified from the context of precision radial velocities. It's a well-known detector effect, but it's something that we really should be following up moving forward, because I think it's an interesting systematic, but we don't really, for example, have a correction for this implemented anytime soon. Okay, so kind of stepping back to the system, we've talked about the detector. In general, I think everyone on the call can appreciate that thermal control is really a critical component of any PRV system. And this is just a kind of a cartoonish example that I bring up just so that, we have something, a leg to stand on, basically. But here's an example of why precise thermal control is critical in general. So if we take a look at arguably the most important dispersive element, certainly, in any EPRV system, which is the shell grating. The grating itself has of course, a dispersion solution that depends on a variety of parameters, several of which, well, actually one of which is largely temperature sensitive. And so if we change the temperature of our grating, we of course change the effective exitance angles of all of our wavelengths, resulting in a net velocity shift. There's a back of the envelope calculation on the right showing that even for a typical very low expansion glass grating like what we all have on Newid, HPF, Espresso, etc., you still need sort of tilde millikelvin level temperature control to make sure that we're not drifting significantly. All of this is, of course, calibratable, but I bring this up as just kind of a cartoonish example of why we need thermal control, and a very precise thermal control. Sticking on that latter point for a moment, this is a set of figures that I think shows a perhaps more useful experiment, which is to say that, well, so stepping back. So this is a set of panels that shows kind of an empirical measurement, or an attempt at an empirical measurement, assessing our actual as-built thermal sensitivity for KPF. I actually did forget that this meeting is recorded, but these are very preliminary results, so please don't share them, but I guess at least until the recording comes out. But at any event, this summary set of slides shows, I think, about a 12-hour window into KPF testing. This was done while we were still at Berkeley before we shipped. On the upper left shows the absolute drift as measured using a thorium-argon lamp of the entire instrument with our various fiber slices. On the upper right shows the thermal variations over that same time period, where this was very, very far from a controlled experiment, but I think it still gives you a sense of there's an obvious correlation here. Causation not equal correlation, but nonetheless, this is giving us some empirical estimate of how sensitive is our complete system to thermal variations. And so on the lower left, I'm showing the differential fiber drifts during the same time period, where at least we're confident that we can remove the vast majority of this absolute drift using our calibration fiber. But if you squint hard enough, you can actually still see some vague trace of this sort of parabolic curvature, which is following the thermal gradients. This makes sense, of course, but I'm kind of highlighting this to say, we have put a lot of effort into, of course, modeling each component thermally and trying to understand how all of our pieces fit together and the thermal sensitivity of the system as a whole. But there's really no substitute for just measuring it in ideally a more controlled way than this. But nonetheless, I think these kinds of experiments are pretty key for further understanding systems, again, at the level that we care about, which is sort of sub 10 centimeter per second. So continuing our sort of reverse trajectory through the system, there are a number of errors associated with just the delivery of photons, frankly. So systems that we use to transport light from our telescope to our spectrometers are imperfect by nature. Optical fibers commonly used to collect light have some memory, I guess I'll put in air quotes, of their incident illumination, at least in the context, or at least for standard seeing limited multimode fiber instruments. And this can be reasonably well propagated to a radial velocity error. Again, this is one area where classically we've relied heavily on sort of bootstrapping of laboratory measurements of just the fibers, standalone fibers, and saying, okay, we believe based on our laboratory measurements that we expect so and so a centimeter per second error based on our guiding performance. That's, I think, a great starting point. But I would argue that an on-sky test is basically the best verification of this. And so On the lower panels here, I'm showing an experiment we did with NUID, where again, we're injecting calibration light into our science fiber through our fiber injection unit at WIN. And then we're purposefully nodding that fiber, the image of that fiber, image of our calibration fiber on top of our science fiber, and trying to assess how sensitive, what is the residual sensitivity left over after all of our scrambling and all of our agitating and so on and so forth. And so the plots below show the measured differential drifts between our calibration channel and our science channel, again, as we're sort of moving our illumination pretty egregiously off center, but maintaining the same signal noise. And so I think the takeaway for this is there's maybe a hint of a detection, especially if you look at the lower right, where the center of that time series is at maximal deviation from center. I think this is generally consistent with a scrambling gain of something like 15,000 for those who are into these kinds of numbers. But again, this is something where measuring it in the system the way that you care about it, i.e. what is the final radial velocity error, I think is really critical as we move forward. Okay, so to further your paranoia, I'd like to focus on the calibration sources we rely so heavily on themselves. So one example of this that I'll go over in a little bit more detail is FebriPro Etalon, which is sort of the workhorse for at least a handful of precision radial velocity systems out in the wild, including Habitals on Planet Finder, including NUID, KPF when we're done with that. At its core, FebriPro Etalon is just two mirrors, it pains me to say, but it's a reasonably simple optomechanical system with an incredible amount of subtleties involved, which I'll get to in a bit. So here I'm just showing a couple of Etalon designs that exist. The top panel shows a layout of the NUID/HPF Etalon design, just in cartoonish form. The lower panels show a rendering of the KPF Etalon and the Maroon X Etalon in its chamber, or some version of the Maroon X Etalon in its chamber. And so there are a lot of these used every single day. And so characterizing calibration sources themselves is also a key priority moving forward, I think. Again, so while we like to think of these Etalons as reasonably simple systems, because we have now such stable measurement platforms, we can kind of begin to see the cracks in these calibrators. And so what I'm showing here is a measure of the internal drift of the Etalon itself. Again, this is the device that we're using to characterize and parameterize drift, but it itself is indeed drifting over time. And so on the left is an animation showing the sort of drift built up over time in the NUID Etalon, which is a reasonably strong function of color, an interestingly sort of pseudo-sinusoidal one, where different parts of the Etalon spectrum are drifting in different amplitudes. And so this is something that we have to characterize and either model out. In this case with NUID, because we cross-calibrate with a laser frequency comb, it's less of an issue, but these are fundamentally imperfect calibrators. Understanding them is another key to success, I would argue. And so on the right, this is from a recent paper from Tobias Schmidt, which is it came out a couple months ago. This is showing a similar measurement for the espresso FebriPro Etalon, seeing after they remove the bulk drift, they see a similar chromatic drift over time. And again, this is something that wasn't necessarily expected, but something that we will have to deal with moving forward. Okay, so zooming back to our kind of total stable of precision radial velocity instruments, this slide is sort of meant to highlight how far we've come as a community, frankly. I would say we've probably invested, just as a total WAG ROM estimate, but over $80 million in precision radial velocity instruments over the past decade. And I would argue that each one of these is a very valuable data point for different design choices, for understanding systematics in different ways. And I would also argue that we're still far from extracting all that we can out of the instruments that we already have before we think about perhaps the next generation, if there is to be one on the horizon. So sort of sticking with that last point, we have converged as a community on a wide variety of design choices. Converge is probably the wrong term because we've diverged quite a bit. But the diversity of designs is pretty spectacular, just from sort of a technological standpoint. So we have designs ranging from all glass designs such as KPF to designs that prioritize conductivity and uniformity and high stability, high thermal stability, such as NUID. We've got composite benches, we've got stainless steel, Invar, gravity-resistant mounting, athermal designs. All of these have been implemented and are now, or will soon be, in the wild and in operation. And understanding the subtleties of each of these designs and how they can help us paint a better picture of what the fundamental limits, frankly, are of precision radial velocity measurements and calibratability, I think is going to be a pretty important exercise moving forward. Because we all have very similar, common scientific goals. I think understanding the instruments at the next level, what sort of, one more order of magnitude, I think will be pretty key for this. So with all that said, I think I want to kind of end it here. This is a slide that's meant to generate some discussion, I hope. But it's what can we learn about the instruments that we have? Are there prospects for activities such as, scientifically, we've been talking about things like observing standard stars with some regular cadence and comparing that kind of data set. I would also argue that, these smaller scale instrumental experiments should be kind of homogenized and perhaps done on multiple facilities if possible, and then notes can be compared to there. But it's how can we best use the instruments that we have to understand basically what's next. Do we continue to implement new reduction mitigation strategies, data reduction pipeline mitigation strategies, that is, new engineering strategies for improving our performance, and how does this all flow into the next generation, again, if there is to be one on the horizon. So I think I kind of want to end it there, and again, make it sort of open-ended, but I'm hoping that we can have a fruitful discussion. So I think with that, I'll take questions, and thank you for your time.
Thank you very much, Sam. That was really, really wonderful. I'm sure everybody would be clapping if we were all in the same room, so thank you. With regards to questions, I'll start with, I see Drake has raised his hand, so we can start with Drake, but also, so please raise your hand or put something in the chat. Go ahead, Drake.
Okay, Sam, that was a very insightful talk, and I really enjoyed that. I have a question that's kind of out of the box. I note that our colleagues in astrophysics that detect gravitational radiation have demonstrated that interferometers can be extremely precise. And one way to measure a spectrum is to measure the path differences with an interferometer instead of a grating. And then you won't have to worry about the grating stability. And that's was historically, of course, has been done with Fourier transform spectrometers. Nobody uses those anymore because they'd have unacceptable efficiency because you're using a single detector and you're measuring the path differences in a serial manner, but they have some tremendous advantages in terms of the spectral purity and the grading. There's no grading, but maybe there's some hybrid approach. Has anyone thought of some completely different kind of spectrometer that doesn't use a grading, that maybe you can use multiple detectors with an interferometer have there anyone thought about anything like that?
I certainly flirted with the idea. I would like to hear from actually perhaps if anyone on the call is part of the heterodyne spectroscopy efforts, because I think in the scheme of how one makes precision frequency measurements, we're doing it in the most passive way possible, right? We're recording a spectrum on a detector. We are simultaneously recording a calibration spectrum, trying to understand our instrument at the same time, but ultimately you're throwing away a lot of the underlying spectrum by not interfering it with either some local oscillator or itself as you need. So are there proof this? I think yes. To hear from other folks on the call about this.
So Drake, this is David. I will say that there was a group led by Jean Gueux who when he was at Florida in particular, tried very hard to get a Fourier transform spectrometer to work in just the mode that you were talking about. And for technical reasons that I don't fully understand, they ran into a whole series of problems and just never could quite get it off the ground.
Mhm.
But I do know that there was a group that had tried that.
Yes.
Yeah,
Yeah, I remember.
so,
Yeah.
So Andreas, did you have a comment directed to Drake's, because Heather was ahead of you?
Yes, yeah. So yeah, I also wanted to point out that there's this externally dispersed interferometry, which tried to use interferometry as the kind of basis. I think there are two important differences with respect to the gravitational wave case. One aspect is that we are using it in broadband and not at a single wavelength. And a lot of the issues we have to deal with are really related to these broadband chromatic effects. Yeah, we could perfectly well stabilize an etalon at one wavelength, for instance, but then the chromatic effects are going to really create problems. And the other thing that is sometimes underappreciated is the fact that we are dealing with, that we are on a moving platform. So our lines shift back and forth in an annual cycle by tens of kilometers per second. And so what we are measuring is not a deviation from a zero. We are trying to measure a deviation from a perfect sine curve. And the sine has an amplitude of tens of kilometers per second. And we are trying to measure a deviation of the order of a meter per second or less. And that's a lot harder because the stellar lines shift against the telluric lines. They shift on the detector by several pixels. So all these things like non-linearities in the wavelength solution, this all plays a role just because we are not keeping things stable on the detector, but we are shifting over time. So I think those two things really are sometimes a bit underappreciated in really making instrumental difficulties.
So that's a coupling of the instrumental aspect and the data aspect of the spectrum you're measuring.
Yeah, and and as I say, you have two spectra superimposed. One is that of the telluric absorption. The other one is the one of the star. And yeah, you are not trying to keep everything extremely stable and have a zero measurement that is purely differential, but you have to, you have to kind of follow the spectrum as it wanders across your detector due to the barycentric correction.
That's why it's interesting.
Okay, so there's a question from Heather Siegel in the chat. Heather, did you want to speak, or I can just read it?
It doesn't matter. Now
okay, go ahead, Heather. Go ahead.
Sam, I was wondering if you could count on how solar telescopes can help us understand our instruments and how important you think they are going forward.
I'll answer the second point in a biased way from the context of sort of just economics. I think solar telescopes are fundamentally critical for any EPRV instrument because they can save commissioning time, if nothing else. But I think from a instrumental perspective, I think their utility has really yet to be, they have very high utility. It's very important that we have them from the context of comparing instruments and assessing our own instruments in a way that's you really can't do without just having celestial photons, right? You need a source that looks like the source you want at the end of the day to assess how well the instruments are measuring a velocity on that. I think, with NUID, we did some reasonably detailed, but I would argue, not far enough detailed assessments of, okay, we're measuring some RMS basically on the sun over a short time scale. And we can say, all right, we think X% of that RMS is because of granulation, given a model, X% of that is because of oscillations, again, given a model, and whatever left over we can assign to the instrument / measurement system. What is that number? And so that's, that's kind of a clunky way, but I think it's the best approach we have. And so from that context, it can give us a pretty quick turnaround on an upper limit for how much the instrument is actually contributing to the overall measurement for, albeit again, you're kind of bootstrapping off multiple models, right?
Okay. Are there other questions? Raise your hand. So Dave Latham, please.
Well, I would like to promote another use of solar telescopes, and that is to compare the velocities between different observatories that are obtained simultaneously, and where you can then take out what the sun is doing and see what's left over for your instrument. Or you compare two instruments, so you know the difference between the two instruments. And if there's routine monitoring of the sun by a whole bunch of EPRV machines, this is, I think, a way of learning about your instrument that is hard to do any other way.
Agreed. And I think, much like we're trying to standardize solar observations, I do think the sort of same set of folks should be looking at common sets of calibrations in similar ways. I think given that a lot of us are now literally using the exact same frequency combs or similar frequency combs, et cetera, have almost the same detectors. I think a lot of the experiments that can assess short and long-term instrumental stability using the sun and not, I think need to be shared in some cohesive way if we're going to move forward. I think a lot of this happens at, things like the EPRV conferences, SPIE, et cetera. But I kind of want to get people's thoughts on sort of what's next. I think solar data is very tantalizing, and that's the next sort of immediate step. But are there other ways that we can use the instruments as sort of platforms for understanding some of these fundamental limits?
So that's a great question to the crowd. Does anybody have an answer to address Sam's question there? Or at least some thoughts?
I'd also preface this with, maybe I'll put out something more provocative, which is all of us that have spent, many years building these things are now using them. And so the focus on the instrument science, I think, has dwindled. I mean, I'm talking from personal experience, perhaps, but obviously we want to do the science at the end of the day. But that, that doesn't leave a lot of room for sort of continually improving on the instrument science. And again, trying to eke out every bit of performance that you can. And so I think if you want to have long-term improvements for the platforms that we already have, there needs to be some kind of community push and some funding perhaps associated with it, dedicated to better understanding and improvement of the instruments just for the sake of the instruments. And I think that doesn't exist yet, as far as I know. But that's another thing I would love to hear some thoughts on, if anyone has any.
So maybe one workshop idea going forward would be, this discussion of, the processes that different groups have done with their calibrations, what they've learned, what they've changed, and how that crosses over from group to group to maybe establish. I mean, every instrument has its own gremlins and has its own personality, but maybe there's some very specific things that would need to be done in common that could be identified or done in a certain way that can help put things on a more comparable scale. Okay, so there's two hands up. The first one I saw was Samantha. If I got it in the wrong order, I apologize. But so Samantha.
Hi, thanks. That was a really great talk. I was just thinking about, we were talking about comparing instruments and solar telescopes, and you mentioned in your talk about laser frequency combs as well. Are we taking maximum advantage of using laser frequency combs? And, for the future, should we be thinking of ways we can be comparing instruments using that? Because ideally they should be a perfect calibrator, ideally with, narrow line profiles and, GPS stability and all the rest of it. So what are your thoughts on that?
Yeah, I think that's exactly right. And given that a lot of the combs that exist are all from a single vendor and they're all quite literally locked to the same signal. They're not exactly the same frequencies, but they're all tied to the same frequencies. I think that's a natural way to get a reasonably homogeneous comparison of important systematics. And so how that shakes out into how best do we all use them, and if there's some standardized set of tests that we can all do that don't take a lot of time or risk any on sky time, I think I'm all for that. I think we should discuss what those are
definitely
way.
Yeah, I'd love to have that, continue that discussion.
So I'd like to point out that Johanna Teskey pointed out in the chat that maybe this is a good topic / splinter for EPRV 5, which is intended to be March of next year.
Yeah, cool.
Sounds great.
Okay, so the next hand I saw, I think was Lily's. I think that came first. If not, sorry, Nathan.
Yeah, I just wanted to say that I was successfully provoked by what Sam had said earlier, where I think separating out the science and the instrumentation would be foolish, right? Because you build the instrument in service of the science, and then as you do the science, you realize that your instrument fails in some way, and you cycle back, and it's more of a cycle than like a step process. At least is what I've been feeling. But I agree that having the input from different instruments would be really helpful, just to give people who work on instrumentation hardware and the data analysis pipelines a space to like think about all the issues they've encountered since they locked up their vacuum chamber, never to be opened again. Because usually it's like a crisis situation where you have to solve something. By the time you're on Sky next, you solve it and then it just fades into memory. But giving people the space to reflect what they've done, the lessons that they really have learned, and contribute that to the group would be a really helpful thing to do, and maybe something to consider for EPRV 5.
Agreed. I think the constant tension, rightfully so, of prioritizing, not risking the system, basically, right? I think is a good one. But it doesn't lend itself well to sort of further characterization at a deeper level. I think Nathan was the last person with their hand up.
Nathan, please.
Yeah, thanks. Very interesting talk. I was wondering, what do you think can be improved on the software side? Like, how much can we gain by improving on the software before being completely limited by the hardware?
That's an excellent, very deep question. I can imagine specific corrections based on some of the tests that I showed, for example. There's always ways to improve things in the software. I say that not really being a software person, so that's not particularly fair. But I think there are algorithmic corrections, at least at the sort of detector systematics level, that could be implemented kind of on the near-term horizon, that would at least solve some of the issues, not solve, but do a better job of containing some of the issues I was discussing. That's very vague, and I have to think about your question deeper to come up with a broader answer, but I think there's certainly still sort of meat left on the bone in a number of ways coming at this from a reduction pipeline perspective.
Mm-hmm.
Okay, thanks.
Andreas,
Yeah,
go ahead, Andreas, please.
a remark about this software, and especially on the last thing, the pipeline. I feel that we have to take a step back from this pipeline paradigm. Actually, Sam, you had some excellent examples where you showed what you can learn when you are able to experiment with the data and look at the data in a non-standard way, namely, for instance, binning by amplifier, things like that. So I would rather like to have something like a data reduction toolbox, especially for diagnosing things in the spectrograph and in the calibration system and so on. I would like to take very different views on the same data, splitting things up by half orders, amplifiers, other things. And many pipelines are written in a way that is too rigid to make that easy to do. So taking more of this exploratory approach would really be helpful.
Andreas,
Agreed.
Seifert, did you have a comment?
Yeah, I mean, tagging on to what Andreas just said is that, you know, we all try to squeeze out, if we can, as much of the performance of each individual instrument. And then a lot of that is basically buried deep in our data reduction codes, mainly into how we actually do derive a wavelength and a drift correction. And so that's all fair. The question is, if we want to learn about the underlying issue of each individual instruments and for the next generation do better, we also have to think about approaching this issue with the same tools. And so having one toolbox that basically allows us to digest data from individual instruments and then you know, try to see the individual gremlins, as David said, and try to get them to know them and try to avoid them if possible for the next generation. That's also, I think, a very, very important task for the community. That is not so much beneficial, I think, for an individual instrument, an individual team, and that's why there's probably a lot of resistance if there is no funding for that on a community level to do that. But I think it's important if we want to move forward from the current generation of instruments to something that will hopefully at some point be able to do these like centimeter per second level measurements.
Agreed. I think it's sort of, it needs to be a programmatic thrust. I think it's not going to come organically. I have to apologize. I actually have a very hard cutoff now. So I have,
No worries.
but good to see everyone. Thanks for your attention and thoughts, and I'm glad we had a nice discussion.
Thank you all for joining, and just a reminder, there's a colloquium in a month. We'll do this again, and so thank you all for the discussions, and thank you, Sam, for the time and presenting.